Our induction formulas, right? So the flux, this is magnetic flux. Okay, magnetic flux is BA cos theta, right? So let's just draw a careful picture of this, right? Here's some area, right? Remember that area is represented by a vector. Here's our area, right? Okay, but the area is represented by a vector that's equal to length times width, right? But it's perpendicular to this thing, right? So then if we've got a magnetic field, let's suppose we've got magnetic field, right? And the magnetic field is like this. At some angle, it's not parallel to that thing, right? Okay, you would actually go and take this angle, whatever this angle is here. Okay, and the very best possibility is that that it's zero. The angle is zero, or I suppose 180 would be give you a -1, right? Okay, that would give us the maximum thing, right? That the area, the ad hoc or whatever area vector that we say is parallel to that, right? If they're parallel, the angle is 0, cos of 0 is 1, and it works out just perfectly. Okay, if they're at some angle, be careful how you measure that angle. Remember that it's a bit like light. The maximum flux is light shining through this loop. Okay, the more light that shines through that loop, the more flux you have, right? And so figure out your angle accordingly. Okay, and then this is magnetic field strength. That's the area of the loop, and then that's the angle that I just described. All right. And then this is Faraday's law. So that's actually one of Maxwell's equations, right? It says that the EMF, that's the EMF, which is like voltage, okay? We could divide it by resistance and get current, for example, right? Is the number of windings, okay, times the change in flux over time. So ultimately, the cell turns into NBA cos theta, right, over time, ultimately, right? Okay, it's like National Basketball Association, right? And remember, this gets tricky, right? The safest thing is to say that it's the number of windings in the coil, right, times BA cos theta minus BA cos theta. Because they could give you a problem where the area changes and the magnetic field changes and whatever, right? And then divide that by the time, right? Okay, and that'll give you the EMF on this thing, right? This is, yeah, there it is, right? And then this is, if we have, let's say we have a magnetic field like this, right? And let's imagine that, so that's a magnetic field out of the page, right? Okay, and then let's imagine that I've got a wire like this. And the wire is moving this way. Okay. Notice that this part, this side of the wire is not in the magnetic field, right? Has already exited, and during that situation, right, as it moves, okay, you would get an EMF induced by this. So here's our L, right? Is this part? The V is the speed with which you're moving it out of there, right? And in this case, by the way, you're losing out of the page, so you would create out of the page and go anti-clockwise in this case. Right? Remember all this stuff, though. It's so good, right? Okay, so we move this thing out of the page. You would figure out the EMF that's operating by going magnetic field times the velocity times that length that it overlaps like that. Okay, now really there is there a, yeah, there would be an angle in there. Evidently they're not going to give you any angle, so, so don't worry about that, I guess, huh? Angle would worry about that. And then this allows for the possibility that in fact this loop might actually be many windings. Let's see if I can draw that without failing. So this loop, instead of being one winding, I was like looking at this. I had to ask other physics teachers. They're like, I've never seen this formula. They're like, you dummy, it's this, right? So if you had many windings and you pulled that thing out, it would do this, right? So it would just be the number of windings times BVL. Okay. Induction, you gotta love it, right? So just remember that the direction of the current, it flows to resist the change in flux. Whatever the change in flux is, it resists it, right? So if you lose flux, you replace it. Be good to look at a few of these, right? And if you gain flux, you oppose. You create flux that opposes the gain, right? Anyway, happy studying.